Welcome to this explainer. Today, we're diving into the first dimension of high-voltage battery functional safety, the battery cell and electrochemical layer. Specifically, we're going to unpack the 101 P080 fault code, commonly known as the weak cell phenomenon. Imagine a massive, incredibly powerful EV battery pack, an absolute engineering marvel, putting out hundreds of horsepower. Now, imagine all of that power being completely brought to its knees by a single microscopic flaw in just one tiny cell. It's a terrifying scenario, right? But it's an absolutely incredible system to study. We're going to explore exactly how engineers design incredibly complex, multi-layered defense mechanisms to stop this exact threat.
Okay, let's dive into this by defining a foundational rule of battery physics. It's called the barrel effect. Essentially, this principle dictates that an entire battery pack's usable energy and its maximum power boundaries are rigidly restricted by its weakest single cell. It doesn't matter how perfectly healthy the other hundreds of cells in the pack are. This one weak link literally dictates the capacity for the whole system. Think of the battery pack like a biological system, and this degraded cell is a pathogen. If it hits its absolute voltage limit prematurely, the whole pack has to stop discharging immediately, or you risk catastrophic thermal failure.
So, here is our roadmap for decoding this today. 1. Root cause analysis. 2. Diagnosis and protection. 3. Design prevention. 4. Process control. And finally 5. Production validation.
Section 1. Root cause analysis, or as we'll call it, the disease. To uncover where this disease actually begins, we really have to shrink down into the micro world of electrochemistry and then zoom back out into the macro world of physical thermodynamics. It's kind of fascinating to contrast these two threats. On the micro level, we're looking at electrochemical pathogens. Imagine a vehicle fast charging in freezing temperatures. The lithium ions just can't intercalate properly, which leads to lithium plating. This is where metallic lithium builds up and forms these sharp, microscopic needles called dendrites. You can think of these dendrites as internal shrapnel that physically pierces the delicate separator inside the cell, causing a microshort. But then, on the macro scale, we have thermodynamic effects. If the cooling system is uneven or a heat-generating component sits too close to a module, you get localized hotspots. Because of the Arrhenius equation, we know heat exponentially accelerates chemical aging. So a cell trapped in a brutal hotspot ages way faster than its neighbors. Its internal resistance skyrockets, and the disease takes hold.
And what does that look like? Well, first, because of those microshorts, the cell develops a high self-discharge rate. It's basically constantly bleeding energy, even when the car is just parked. Meanwhile, inside the cell, the solid electrolyte interface, or SEI layer, thickens permanently. This locks up active lithium, which engineers call loss of lithium inventory, and creates microscopic cracks in the electrode, resulting in loss of active material. The physical capacity of the cell literally withers away. During a hard acceleration, this degraded cell is going to experience a dangerous, sudden dynamic voltage drop, a voltage cliff, and that translates directly to suddenly losing precious highway range or even abruptly losing power right in the middle of a highway overtake.
Section 2. Diagnosis and protection, otherwise known as the immune system.
If the weak cell is the pathogen, the battery management system, the BMS, acts as the vehicle's immune system. It's constantly hunting down this sick cell before it can cause a catastrophic failure. The really crucial part here is how the BMS actually catches the culprit amidst all the electrical noise of a moving car. It uses what's called cell tracking logic. Every few milliseconds, the analog front-end chip pulls the voltage of every single cell, looking for a very specific damming pattern. If a cell is flagged as having the lowest voltage when discharging, meaning it's the fastest to run out of energy, and then when you plug the car in, it's flagged as having the highest voltage because its capacity is so tiny it fills up instantly, while the BMS zeroes right in. It catches the cell acting as both the fastest to empty and the fastest to fill. To be absolutely sure, it triggers a maintenance balancing routine to try and heal it. If it can't be healed, bam, it permanently writes the P080 fault code.
The moment that P080 code is confirmed, the fail-safes slam into place. The very first action? Prohibiting DC fast charging. This is absolutely crucial. Jamming massive amounts of high-rate current into a degraded cell with high internal resistance is just a recipe for extreme heat and thermal runaway. The system simply cuts off rapid charging to neutralize the fire risk, because, let's face it, nobody wants their commute to end in a fireworks show.
But it doesn't stop there. As its first stage of active power derating, the BMS instantly slashes the maximum available charge and discharge power of the vehicle by exactly 50%. The system is intentionally handicapping the vehicle's performance right then and there to keep the stress on that weak cell as low as physically possible.
And if the situation deteriorates further, say that 6 cells voltage violently drops below the 2.5 volt under voltage limit while driving, the system has to react immediately so the driver isn't stranded on the highway. Pure EV mode is forcefully disabled. The vehicle coordinates with the central controller to drop into a hybrid electric limp-home mode. Speed is strictly capped at or below 50 kilometers per hour, and your dashboard lights up with the malfunction indicator and that dreaded turtle warning light. It is a sudden, aggressive intervention to ensure physical safety.
Section 3. Design Prevention. This is the DFMEA phase, or building the wall.
So that's how we handle the fault when it happens, but how do we prevent it from ever occurring in the first place? This is where engineers build the ultimate vaccine, before the battery even physically exists. Remember those macroscopic thermodynamic hotspots we discussed? To prevent them, design engineers use advanced computational fluid dynamics to optimize the internal liquid cooling channels. Their strict design target is absolutely incredible. The temperature gradient across the entire, massive battery pack must be maintained at less than 3 degrees Celsius. By eliminating physical dead zones in the cooling system, they ensure no cell gets left behind to age faster than the rest.
Because a P0A80 fault is so disruptive, in the DFMEA risk assessment, it gets a massive severity score of 8 out of 10. A threat this high demands heavy-duty countermeasures. Engineers mandate incredibly strict cell sorting algorithms so that only perfectly matched cells are paired together at the factory. Furthermore, they often implement robust active balancing circuits capable of transferring more than 1 amp of current between cells. This gives the system the physical muscle to dynamically compensate for tiny inconsistencies over a long lifespan.
Section 4. Process Control. Moving into PFMEA, or Factory Defenses.
Stepping onto the actual factory floor for the PFMEA phase, the goal is strict, uncompromising control to stop microscopic variations during mass production. Every single step of manufacturing has a dedicated error-proofing mechanism. During formation and grading, 100% of cells undergo dynamic K-value screening to catch any tiny self-discharge rate anomalies that might hint at a micro-short. Electrode manufacturing requires an ISO Class 6 clean room to prevent dust and strictly limits metal burr heights so nothing can puncture the separator. And during module assembly, fully automated systems measure the open circuit voltage and internal resistance of every single component, permanently tying that data to the cell's barcode in the manufacturing execution system.
To prove these factory defenses are actually working, manufacturers rely on hard statistics. They enforce a Process Capability Index, or CPK, of 1.67 or higher. In statistical process control, a CPK of 1.67 is the gold standard. It basically means the manufacturing consistency is so incredibly tight that the chances of an outlier, defective cell making it into a finished battery pack are vanishingly small.
Even the physical assembly of the pack is scrutinized at a microscopic level. For instance, the impedance of the busbar connections, those metal plates linking the cells together, must be strictly measured and kept under 0.05 milliohms. Literally just a tiny fraction of a milliohm of extra resistance from a bad weld would generate localized heat during driving. That throws off the delicate thermal balance we talked about and slowly cooks the adjacent cell, which ultimately degrades the vehicle's lifespan and hits the driver right in the wallet when the pack needs replacing.
Section 5. Production Validation, the DVP&R phase, or the final exam.
So we've designed a perfect system and built it in a perfect factory. But before any of this goes to the consumer, engineers run brutal simulations to ensure the BMS reflexes work flawlessly under immense pressure. One of the most critical validation tests ensures the BMS isn't falsely crying wolf. It has to perfectly distinguish between a temporary soft imbalance and actual hard degradation. Engineers will intentionally feed the BMS a simulated soft imbalance, say a 120 millivolt difference caused merely by a software calculation drift. The BMS must successfully trigger maintenance balancing and heal that gap to under 20 millivolts without throwing a code. Then they hit it with a physical microshort simulation. The gap fails to heal, the voltage drops rapidly under load, and the system must correctly and permanently lock in that P0A80 fault code.
Finally, engineers test the system's reaction time to a catastrophic mid-drive event. The fault-tolerant time interval is an incredibly tight window to prevent disaster. Let's look at the timeline. At time 0, a weak cell's voltage falls off a cliff to the 2.5 volt under voltage limit. Within half a second, the BMS must confirm the P080 fault. By 1.5 seconds, it must broadcast power derating commands right across the vehicle's CAN bus. and exactly at 2.0 seconds, the vehicle control unit must physically limit the motor torque, engaging limp-home mode safely without abruptly jerking the car or causing a total loss of power on the highway. Literally, 2 seconds to save the vehicle.
And that brings us to our final thought for this explainer. We've tracked the P0A80 fault from a microshort in a single cell through the rigorous algorithms of the BMS all the way to those brutal 2-second safety responses on the road. When you consider that a single, invisible metallic burr has to be stopped by an immense cascade of clean rooms, thermal optimization, software tracking, and limp-home protocols, it really makes you wonder, is the creation of these high-voltage battery systems merely a strict science, or has it become a highly demanding, completely uncompromising art? Thanks for exploring this with me. I hope it gave you a powerful new perspective on the invisible engineering keeping us safe on the road.